Ooh, that was a Mrs. Doubtfire hello, but hello and welcome to 3-2. We talked last time about exponential functions and their graphs. Today we're going to talk about logarithmic functions and their graphs. The definition of a logarithmic function: when x is greater than 0 and a is greater than 0 and a does not equal 1, y will equal, zoom in here for you, y will equal the log of a to the x if and only if x equals a to the y power. The function is given by f of x equals log base a of x. It is called the logarithmic function with base a. There is an important relationship here. Okay? I'm just going to jot it out. This is the most important thing. Log with a base of a of x equals y, and a to the y power equals x. This is absolutely key. This will help you in solving logarithmic equations like you wouldn't believe. Okay? This is basically, and as you're going to see, logarithms and exponents are kind of like inverses of each other. That's how they're so closely related. You know, think of it almost like the relationship of the square root and the squared, how they're kind of opposite of each other, but when you do one to the other, it kind of takes out the other, and you have that kind of relationship there. That is the same type of relationship of closeness. Where you have an exponent, you have a logarithm, and where you have a logarithm, you have an exponent, potentially. Let's take a look at these first problems. Use the definition to evaluate each logarithm. So the first one, we want log base 2 of 32. It equals something. We're going to call it y. So now I want to ask myself, if I rewrite it in exponential form, 2 to the y power equals 32. So now I need to find some number that when 2 is raised to that power, it will equal 32. Well, I know 2 squared is 4. So 2 squared is 4. 2 to the third power is 8. 2 to the fourth power is 16. And 2 to the fifth power is equal to 32. So therefore, log base 2 of 32, not 33, equals 5, because 2 to the fifth power equals 32. Okay? Let's try B, and I'll try writing a little bit smaller this time. Log base 3 of x, log base 3 of 1 equals, we'll say, y. So 3 to what power will equal 1? Well, if I raise any number to a certain power, they will always equal 1, no matter the size of the number. And that is because 3 to the 0 power equals 1, which means, therefore, y equals 0. So we can say log base 3 of 1 equals 0. So in this problem, I'm basically asking myself, when I have a base of something, and I want to find out what it all equals, I'm saying, what is the exponent such that the base raised to that exponent gives me the answer I'm looking for? Okay? So log base 4 of of 2 equals what? So 4 to what power will equal 2? Well, I know 2 squared is 4. And I know the square root of 4 is 2. So what that will mean, and we've talked about this in class, is that 4 to the 1/2 power will equal 2. Remember, when I have the square root of 4, that is the same thing as 4 to the 1/2 power. If I have the cubed root of 4, that's same as 4 to the 1/3 power. So we would say that log base 4 of 2 equals 1/2. And finally, log base 10 of 1 over 100 equals y. Well, 10 to what power equals 1 over 100? Now I'm going to use two properties of exponents that I know. First of all, 10 to what power equals 100? Well, 10 squared is 100. But I can't just have 100, I have to have 1 over 100. So what that'll tell me is I will have 10 to the negative 2 power equals 1 over 100. Because anytime I have a negative exponent, it flips it from top to bottom. So the answer of 10, log base 10 of 1 over 100, it equals negative 2. Now, evaluating some common logarithms in the calculator. You have a log button in your calculator. Let me make this clear. The calculator log button is set to log base 10 of something. So the calculator is already set up to do a log base 10 of whatever you type into it. So when you press the log button, it's assuming that you're doing log base 10. Not log base 3, not log base 2, not log base 4, not log base 1, not log base anything other than log base 10. But if all you see is log of something, it is automatically understood that you are dealing with log base 10. Okay? So use a calculator to find basically the log of each of these. Log base 10 of 10, log of 1/3, log of 2.5, and log of negative 2. So I would come to the calculator and I would literally type in log 10, enter. And it would give me 1. It would give me log, and then in parentheses I'd put 1 over 3, and then I'd put enter. Then I do log 2.5, enter. Log negative 2, enter. Notice with negative 2, it gives me an error. The reason why that this one would give you an error is because I'm basically saying log base 10 of negative 2 equals what? It's saying 10 to what power is going to give you a negative number. What this is teaching here is an important lesson that you can never take the log of a negative number. You just can't do it. You just cannot do it. It is not possible. Why? Because you're never going to get a negative number. Because there's no way that you can raise 10 to a power to become negative 2. Now, there may be some way you could raise negative 10 to a power, but there's no way that you can do a log of a negative number. Some properties of logarithms. Okay? Number 1, if I have base A, if log base A of 1, it will always equal 0. If I have any base that is A, it doesn't matter what the base is, it can be log base 10, log base 20, log base a billion, and the next number above it is 1, then it always equals 0 because of A to the 0 power equals 1. Remember, we're basically saying this to this power equals that. So no matter what it is, if your log equation equals 0, then you will always have a 1 there, and if it's log base something of 1, it always equals 0. Now, if you have log base A of A, in other words, you have the same base as you do the next number, then it will always equal 1. Why? Because you're asking what A to what power equals itself. Meaning, A to the first power equals itself. 3 to the first power equals 3. A billion to the first power equals a billion. So if I had log base 3 of 3, it would equal 1 because of that. Now, if I have log base A and then I have a to the x power as my argument inside there. A to what power equals a to the x? What basically happens is this cancels out because it's an inverse of itself. It cancels out. So, in other words, if I had log base, let's call it log base 3 of 3 to the x, it would equal x, because if I didn't know what that was, I'd say 3 to what power equals 3 to the x. Well, now I have a 1-to-1 situation where it simply drops. So when I have log base a and I have the same argument with an exponent, then it automatically just simply is whatever that exponent is right here. Now, if I have a and it's raised to the same, the a is raised to the log base, and the base of the log that it's raised to, and the exponent is the same as the base of the exponent to begin with, then it simply cancels out. So in that case, that would be, I don't know why that's writing rather than erasing, that would be like 3 to the log base 3 of x, with this being an exponent. Well, basically, because you have 3 and it's raised to a log with the base of 3, that just becomes x. It all cancels out. One thing I should teach you, an expression that you will hear from me, and you've maybe heard it from other teachers. If you haven't, then I guess they're just not cool. And that is with the first one, something that we were taught when I was in school, is if I have, let's say, log base 3 times 3 to the x, whatever this exponent is, if I have an exponent of the argument of the logarithm, it's called rolling off the log. Okay, and I can move it to the front and then just write it as, not x equals, x times log base 3 of 3. That may come up in the next section, but I wanted you to be aware of it anyways. And then the 1-to-1 property, if I have log base a of x and it equals log base a of y, then x equals y. If the bases of the logarithm are both the same and they're equal to each other, then their arguments must also equal. So simplify these problems. Log base 4 of 1 equals what? Well, remember, we're basically saying 4 to what power equals 1. Okay, we go back to our properties. That is the first property. It will equal 0. Because 4 to the 0 power equals 0. So log base 4 of 1 equals 0. Okay, so if I ever see a 1 right there, I automatically know the answer to it is 0. The next one is an example of, oops, I went too far ahead page. The next one is an example of property number 2. Notice I have a base and an argument that are the same. So log base square root of 7 of square root of 7 must equal 1. Why? Because if I say the square root of 7 to what power equals the square root of 7, because it's this to this power equals that, then I just simply have to conclude that y equals 1. So therefore, log base square root of 7 of square root of 7 equals 1. That's rule number 2. And then finally, the third and fourth rule comes to play here. I have 6, and it's raised to the log base 6 of 20. Well, these cancel out because I have an exponent being raised to the log of the base, that the base is the same as the exponent. So my answer just becomes 20. So 6 to the log of 6 base 20 equals 20. Using the 1-to-1 property, notice log base 3 of x equals log base 3 of 12. Well, remember, the one-to-one property, our fourth property that we just talked about, basically says that whatever the base is, if they're the same, and it's log base of something equals log base of something, and it's the same base, then I just drop the logs in their bases. And just simply the arguments are equal to each other. So, graphs of logarithmic functions. What we've done here in this first one is we have said in the same coordinate plane, sketch the graph of y equals 2 to the x and y equals log base 2 of x. Notice that they come to mirror across this line y equals x. What is clear here is that they are inverses. We learned about inverses in lesson 1-6. If you review that video lecture, we know that any function that when plugged back into another function and they simplify to equal y equals x, then they are inverses. What you have here is you have a perfect inverse of the two functions. So when x equals 1, 2 to the x power, 2 to the first power is 2, and log base 2 of x equals 0. Because 2 to what power, or 2 to what power would equal, when I plug in 1, 2 to what power would equal 1, and that's 2 to the 0 power. So I would get here, I would get 0. But notice how my graph, one key thing that's different here is that it does cross the x-axis, but it does not cross the y-axis. So what is extremely important here, and we talk about it on the next problem, says sketch the graph of the common logarithmic function y equals log to the x and identify the vertical asymptote. Well, without a calculator, we can plug in and say, well, I know that if I plug in, if I plug in and I have log base 10 of 1 over to 100, then it is negative 2. If I have log base 10 of 1 over 10, it is negative 1. Log base 10 of 1 is 0. Log base 10 of 10 is 1. And so I kind of get this slight curve up. But notice that no matter how far it gets going down, it is just getting increasingly smaller as a decimal, but it is never hitting 0. Some of them that they plugged in with a calculator here. When I take log base 10 of 2, or just type in log 2, I would get 0.301. Log of 5 is 0.699. Log of 8 is 0.903. You can see that it will go up as high as we want it to go, but it can never go down to the point that on the x-axis it becomes 0. It can never ever go down. I'm sorry, on the x-axis that x can equal 0. Okay. So very important. Very important that it never goes. It'll get increasingly smaller as a decimal, but it will never get to 0. Now we get to next the natural logarithm. The natural logarithm, I have drawn the graph up here, copied the graph for you, of it with its inverse. The natural logarithm is basically a log with the base of the natural number e. And it functions just like a regular logarithm. All the properties apply, and it basically gives it its own properties because of that. But basically, any natural log, it has a base of the number e. And so anytime it's just log base e, but we call it the natural log. Okay? Natural logarithmic function. So use a calculator to evaluate these functions given for f of y equals ln of x for each value of x. I would literally, there's a button on the calculator that's called ln. So if it's a natural log of 2, I would type in the natural log 2, enter. Natural log 0.3, enter. When I try to do -1, it doesn't work. Why? Because you can't go negative. Remember, the restriction on the graph we just talked about of the log graph of its parent function, there's no way to go to -1 unless it's been translated over, and we do not have that. Natural log of 1 plus the square root of 2, I would just type in natural log, and then I'd put parentheses, 1 plus square root of 2, and then enter, and it gives me an answer. You're using a calculator for these, nothing else. This is not something you're going to go figure out without a calculator. Not going to happen. Properties of natural logarithms, they're the same as the other ones. Just natural log of 1 is 0 because e to the 0 power is 1. The natural log of e is 1 because you're basically saying e to what power equals itself? Well, e to the first power equals itself. The natural log of e to the x equals x, and e to the natural log of x equals x. The inverse properties, they still apply. It's just in this case, we're using a base of e. And if the natural log of x equals the natural log of y, then x and y equal each other. Okay? You can use properties of natural logs to simplify each expression. So the natural log of 1 to the e natural log of 1 to the e, well, we rewrite this and reduce this back down to what it was, and that is a -1 power. Remember, when I have a negative exponent, it causes whatever the argument is, the base, to go into the denominator. So now I'm saying e to what power will equal -1? Well, this just simply drops it, and I get -1 as my answer. Because now I've got a base e of another e raised to the -1 power, and this whole part of it here just becomes eliminated. When I have the natural e to the natural log of 5, well, on that one, I'll write it in a different color. E to the natural log of 5, remember, I've got a base e here, an imaginary base e, that I just leave out, but that's understood. And so this entire part just cancels out, and I get 5. Next I get the, let's do red, the natural log of 1 divided by 3. Well, according to these properties up here, property number 1, the natural log of 1 is always 0. So I get 0 over 3, which is just simply 0. And finally, 2 times the natural log of e. Well, the natural log of e is just simply 1, which then gives me 2. Easily simplified. Finding the domains of logarithmic functions. Well, what I have here is an example of when you can do some transformations. So, just like with any other function that we had when we dealt with in 1-4, transformations of function, and it might be helpful to review 1-4. But notice when I've got a -2 in here, well, because I've got -2 in there, and I know that it's going to then go to the right 2 units, it would follow that it would go, the domain, the new domain, would be from 2 to positive infinity. The original domain of just a natural log or logarithmic function is going to be 0 to positive infinity because of that vertical asymptote. But because I went -2 there, it basically causes it to go to the right 2 units. So the new domain is 2, infinity. Because the natural log of 2 minus 1 is defined by 2 minus 1 is greater than 0, then it would follow that the graph would be shown by going from negative infinity to positive 2. Now what's key here in this case is this negative x. Because of this negative x, remember, as with an exponential function, it flips it on the y-axis. It does the same thing here. But so then what's happening is it's flipping it on the y-axis, and then it's moving it over 2. So it moves it over to the right 2 and flips it on the y-axis, and so that causes it to get messed up. And then finally, the natural log of x squared. Well, x squared is defined by being x squared is greater than 0. So it must have all real numbers. Because, and this is what's key about this, you may say, well, why do I have this graph and this graph? The reason why I can have that is because when I perform the operation of any number squared, it becomes positive. Okay, so as a result, when I have the natural log of x squared, it gives me two perfectly mirrored graphs. Because if I plug in -1, I'll get 0, and if I plug in 1, I'll get 0. But the only restriction is that it cannot be x equals 0, because that is a vertical asymptote. Because you can never have the natural log of 0. It is impossible. And that concludes this lesson. Sorry it was a little bit longer.